Hello and welcome to Calculus tutorial. We are continuing our look at implicit differentiation. Last time we took a look at two shapes and now we've got two more, triangles and cones. So we're again going to be using implicit differentiation and applying that skill to related rates. And so we're going to have some word problems that deal with triangles and cones and having different rates that are related to each other. So first, let's take a look at one that involves triangles. So a ladder 15 feet tall leans against a vertical wall of a home. So one thing you always want to do is, draw a nice picture of this. We've got our house, and then we've got our ladder that's leaning against it. I'm going to draw it nice and diagonal here. That way you can really see the triangle going on. There's my ladder. And the bottom of the ladder is pulled away horizontally 4 feet every second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 9 feet from the wall? So it's going to be pulled out until this is 9 feet down here. And so the first thing here is, because we have a triangle, it may not be super obvious what equation we're going to use. There's lots of equations. And so you have to realize we're not talking about the area of this triangle. We're talking about the sides of this triangle. So what equation do we know for the sides of a right triangle like this? A squared plus b squared is equal to c squared. And because we're going to take a look at all the rates, one thing you might want to do is list out your variables. So we're going to have an a, b, and a c. And so label this. Doesn't really matter which one is a or b, certainly, but it does matter which one c is. So think to yourself, is a going to be changing? Well, as you pull this way, the ladder is going to fall down the house. So a is going to change. Is b going to change? Well, definitely, because we're pulling this ladder out this way, this distance is definitely going to get bigger. So there is a db dt. Then think, is c going to change? Hopefully you can see there that it's not. The ladder cannot get bigger, longer, or shorter. So there is a dc dt, but we know what it is. It's 0. Let's see. dA, is A going to change? Yes, it is. Do we know what that is? How fast is the top of the ladder sliding down? We don't know what that is. Do we know what dB dt is? Yes, we do, because it's being pulled away horizontally at 4 feet per second. So this number right here is changing at 4 feet every second. All right, do we know any of A, B, and C? Well, we know what C is. That is 15. B, we're going to plug in 9 eventually. And A, we don't know what A is yet. Now, we do need to be careful. We cannot plug in these numbers yet. Because we have derivatives, we can't plug these numbers in until we've taken the derivative. So let's take the derivative of both sides. So the derivative of this side with respect to time, and the derivative of this side with respect to time. Now this is pretty nice because we have addition. There's no product rule. One nice thing about triangles. So the derivative of a squared is 2a. But again, the variables don't match. So you have dA dt plus b squared, the derivative of that is 2b. And then because the variables don't match, dB dt is equal to, over here we have 2c just like the other ones, dc dt. And then we can plug in everything that we know. The one nice thing, because dc dt is 0, all of that goes away. And we're just left with 0 on the right. Let's see here. B is 9, and dB dt is 4. So 9 times 4 is 36, times 2 is 72. Now over here, we're stuck a little bit. Do we know what dA dt is? No, but that is what we're trying to find. So that's going to stay there. We want to figure out what that equals. Do we know what A is? We don't know what A is. And so we have to figure that out. Thankfully, we can. This is just a right triangle. The bottom is 9. The hypotenuse is 15. And so, yes, we should be able to figure out what A is. So just on the side, we got to calculate that really quick. So A squared plus 9 squared is equal to 15 squared. Sorry about that. So let's just finish solving this. 15 squared goes over here. So that is A squared plus 81 is equal to 225. Subtract 81 from both sides. You'll get 4 and 164. Square root both sides. And let's see, the square root of 164 is 12.8. So not a nice number. Square roots rarely are. Oops, I forgot what it was here. 12.8. So A is equal to 12. Wait, I got that wrong, didn't I? Minus 80. That should be 144, shouldn't it? Oops. Well, that's nice. So it's just 12 even. Done and done. Got to make sure you got your math right there. All right, so A is 12. So we have 12 times 2, which is 24. Make sure you multiply by that too. So subtract 72, divide by 12, you get dA dt is equal to 6, it looks like. What are our units? So distance is being measured in feet. And because we are a rate, we are feet. Time is measured in seconds. So our bottom is being pulled out at 4 feet per second. And when the ladder drops all the way down to being 9 feet away from the wall, it is 12 feet up, it looks like. It's a long ladder. It's going down at 6 feet per second. That is how fast it is moving. All right, so that's kind of how we can use that for triangles. Again, you're just taking the derivative of your formula and then plugging in everything that you know. And as long as I gave you enough information, you should only have one thing left over that you're solving for, and hopefully it's the thing that you were trying to find. If not, go back and look at the information you're given and what you're trying to find. All right, so we got triangles out of the way. Those are a popular one. One more shape we want to take a look at. Cones. So cones are usually a little bit harder, but it's a popular one as well. So a cone, vertex down, with a height of 10 inches and a radius of 2 inches, is being filled with water at a constant rate of 2 cubic inches per second. All right, so it's being filled. So we have a cone. It says vertex down. That means it looks like this. All right, the height is 10 inches. And the radius at the top is 2 inches. If you remember, the volume of a cone is 1/3 pi r squared times height. And so we're going to have V, we're going to have R, and we're going to have H. And we're going to have dV dt. We're going to have dr dt. And we're going to have dH dt. Let's see. How fast is the surface of the water rising? So how fast is our water going up? Well, that is going to be dH dt. So that's what we're trying to find. When the depth of the water is 6 inches, that means the height is 6. Let's see, what else do we know here? The water is being filled at a constant rate of 2 cubic inches per second. That is the change in volume. It's how much water we're putting in. So dV dt is 2. Now, one difficult thing about cones is they have this. The height is 10 inches. Then why did I put 6 here? Well, the whole cone has a height of 10 inches. But our water, or whatever we're putting in this, does not have a height of 10 inches. And so we can't put 10 for the height because that's empty space. This is our actual volume. So 10 is not the height. And the same thing with the radius. Yes, the top has a radius of 2, but that is not what the radius is right here. So we have this formula, volume is equal to 1/3 pi r squared times height. As you can see, we don't know a whole lot here. And so what we have to do is get rid of some variables. And cones have an interesting property. They have self-similar shapes when they're being filled. So what I mean by that is if I think about this cone and think about the triangle here that it makes. Okay, I'll put the triangle in a different color here. Think about this triangle right here. And then if I only fill that up a little bit and think about this triangle there, see if I can make it actually look like a right triangle. There we go. Those two triangles are similar. In the English definition of the word, they are similar, but also in the mathematical definition of being similar. So if I told you that the entire height was 10 and the radius was 2, and then I told you the smaller one had a height of 5, what would the radius here be? And hopefully you could tell me it would be 1. They have to be proportional. 10 over 2, 5 over 1. The sides are proportional. Okay? Or if we think about R over H for one triangle must be the same as R over H for the other triangle. The sides are proportional. So, if the whole cone has a radius of 2 and a height of 10, we get the proportion 2 over 10. That must be equal to that same proportion for the actual amount of liquid. Okay, over here. Which is what we're actually concerned about. Okay, R over H. And so what we're going to do is we're going to use this proportion and we're going to substitute one of the variables. That way we'll only have H's or we will only have R's. And that will mean our equation gets much simpler. Because as it is right now, if I take the derivative, we have a product rule. But if I can get rid of a variable, we won't have a product rule anymore. We will have just a regular old power rule, it looks like. So what are we interested in? We are interested in h. So that means I want to get rid of r. So get r by itself, multiply by h to both sides. So r is equal to, let's see, 2 over 10 is the same as 1 over 5, so 1h over 5. So you can even put that over here, h over 5, if you want to. Now that is going to make our jobs a whole lot easier, because now volume is equal to 1/3 pi, our radius is h over 5 squared times h. And just a little bit of manipulation here, this becomes 1/3 pi h squared, and h makes h cubed over, don't forget that the 5 is squared also, 25. And if you wanted to go one step further, actually don't go one step further, don't combine those fractions, and you'll see why. Now this is going to be a very easy derivative. The derivative of v with respect to t is equal to, take the derivative of this side. Now, the 1/3 pi is just a number. The divided by 25 is just a number. The only actual variable we're taking a derivative of is h cubed. So the 3 multiplies down in front, and it cancels out the 1/3. So we're going to have pi. On the bottom, we're going to have 25. And on the top, we're now going to have h squared times dh dt. And then we're going to plug everything in, and looks like we are looking for dh dt. So everything else should go away. dv dt, 2. h, 6. So 6 squared is 36 over 25 times dh dt. Let's see here. To get dh dt by itself, multiply by 25 and divide by 36. So dh dt will equal 50 over 36. Wait, where'd my pi go? Sorry about that. The pi is on top. Don't forget the fact that there is a pi there. So we'll have 50 over 25 over 36. So we're multiplying by 25. That gives me the 50. Divide by 36 pi. And what are our units going to be? Height is in inches per, time is in seconds. 50 over 36 pi inches per second. If that is not satisfying to you, let's change that. What do we get? 50 divided by 36 pi. So pi is right there. Make sure that pi is in the denominator. 0.442. 0.442 inches per second. All right, so there we have a cone example. Definitely a little bit more complicated, but hopefully that clears things up if you were having trouble.